All right, this is number 2 off the net torque worksheet. So we got a string wrapped around this pulley. This mass here is 0.3 kilograms. All right, look. Oh, I got to turn the screen on. Okay. All right, there we go. All right, so look. The way I did this problem, I did A first. Then I solved for D second. In fact, I was looking at this. I'm like, how? I didn't write this. This is a McGehee worksheet. How would you do B? This is a physics. I don't know. I'd have to think about it more. I went like this: 1, 2, and then from there we can find the tension. 3, then find the torque. 4. Like that. I would go in, that's the order I'm going to go in solving this. So the first question is very easy. Find the moment of inertia for the disk. So part A, for a disk, the equation for the rotational inertia. Moment of inertia and rotational inertia are the same thing. The new term is rotational inertia. For a solid disk, it's 1/2 mr squared. So the mass of the disk is 5 kilograms. The radius is 0.6 meters. Like that. So this comes out as 0.9 kilogram meter squared. Okay, now let's skip to part D, the downward acceleration of the mass. Now look, one thing I want to point out, so what's providing the torque on this wheel? Well, we have this mass hanging here, so we have mg down for the mass, and then we have tension up. And then here we have tension down. Will the tension be equal to mg? It will not. They're not going to be equal to each other because why? This 0.3 kilogram mass is going to be accelerating downward. If the 0.3 kilogram mass is accelerating downward, what's going to be larger? Mg or T? Mg. So you can't just say that the tension is equal to the weight of the mass. So what we have to do is we got to set this up. So let's shrink this down here. I'm going to get rid of this calculation. Then we'll make this a little bigger. All right, so what we're going to do is we're going to go to the disk, and we're going to sum the torques. So how many torques are acting on this disk? Just one. The axis is right here in the middle. The only torque on the disk is that tension. Okay? So the torque is going to be tension times radius. The sum of the torques is equal to I alpha. So that's one equation. Now, we go to the mass, the hanging mass, and we sum the forces. Now make the direction of the acceleration positive. Say down is plus, up is minus, like that. So we're going to say mg minus t equals ma. Now one thing we have to do is we have to relate the angular acceleration to the linear acceleration. So a point on this disk, on the perimeter of the disk, this point right here, as it starts to go fast, as the disk starts to go faster, 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 the disk has an angular acceleration. But if you think about it, what's happening to the tangential velocity? For a point on the perimeter of the disk, as the disk goes faster, 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 what's happening to this tangential velocity here? It's increasing, which means we have a angular acceleration, right? There is tangential acceleration. If you have an angular acceleration, if the disk is going faster, faster, faster in an angular sense, that means that a point on the perimeter is going to have a tangential acceleration because the tangential velocity is changing. Does that make any sense? Okay, so this tangential acceleration equals the angular acceleration times the radius. So that's how you connect these two right here. So we're going to go linear acceleration equals angular acceleration times radius. So angular acceleration is linear acceleration over radius. So we're going to take this and we'll plug it in up there. So the angular acceleration is equal to the linear acceleration over the radius. So this is going to be I, A over R. So now we have A in both equations. Okay? So then what I did is I substituted these two equations together. So it's just, all this is now is two equations, two unknowns. What are the two unknowns here? T and A. So dudes, I'm not going to solve, you guys can solve algebra, take two equations, substitute them together. When you substitute these together, you find out that the tension is 2.68 newtons. And then the acceleration, the linear acceleration, is 1.07 meter per second squared. And then let's go ahead and do the angular acceleration. Using this equation, the angular acceleration would be the linear acceleration over the radius. So 1.07 meter per second squared. The radius is 0.6 meters. So we have an angular acceleration of, comes out as 1.8. All right. So now we've answered D, we've answered E, we've answered C. Oh, into the page, you got to use the right-hand rule. You curl your fingers in the direction of the acceleration of the disk, and your thumb points into the page. All right, now let's answer B here. How do we answer B? What is the net torque on the disk? Well, we know what the tension is, right? We now know what the tension is on the disk. This tension here was 2.7 newtons. So the torque on the disk, we're just going to go tension times radius. So that's 2.7 newtons. The radius is 0.6 meters. So that's 2.7 times 0.6. 1.6 newton meter. And there is no other torque. There's no other torque, so that has to be the net torque. Okay, so now we've answered this. Okay, the last two questions are simply what? Kinematics. The distance that the object falls in 2 seconds. So to do that, we'll go, so we're solving part F right now. X equals 1/2 AT squared plus V initial T. V initial is 0, so this is 1/2. Our linear acceleration is 1.07, which right here is rounded to 1.1. And then what do they say? 2 seconds. So it falls a distance that should come out as 2.1 meters. Let me check that. 4 times 1.07 divided by 2. Yep, 2.1 meters. And then lastly, the angular velocity of the disk at 3 seconds. So we can do a rotational kinematic. Angular velocity final equals angular velocity initial plus alpha t. Initial angular velocity is 0. So our angular acceleration was 1.8 radians per second squared. So 3 seconds later, the angular velocity is going to be 5.4 radians per second. And just like angular acceleration, you use the right-hand rule. You curl your fingers in the direction of the velocity, and your thumb points into the page.